effect that I'll talk about later. And it can also be adapted to maintain agent privacy. So, what is multi-agent forward search? Basically, it's forward search where each agent has its own search space. So each agent has its own open, close list, it expands the node using only its own actions. And what makes it multi-agent search is the fact that when an agent expands a state that is relevant to some other agent, it sends that state to the other agent. And that state enters the open list of the other agent, and they continue to search as usual. If you need also to ensure optimality in the search, you need to add some tweaks like optimality, distributed optimality detection, but we're not going to get into it, but you can do that. So it's, well, arguably the best guard method with the appropriate heuristic function. And originally, again, thanks to certain aspects of the distribution, which have a certain pruning effect, it was able to solve problems that you couldn't solve with a single agent plan. Optimally. Okay, so let's look at I said it can work for any search algorithm. Let's look at multi-agent distributed A star. So each agent performs the following. It initializes its open list to the initial state and the closed list to an empty list, and it repeatedly does the following. It retrieves the first node from the open list. If it's a solution, it performs a certain distributed optimality detection algorithm. Otherwise, it expands the node with its own operators only. And it will then compute the age value of the newly generated children, adds them to its open list, and if one of the children, say n prime, if n prime is one of the children of the node that was expanded, and it was obtained by applying a global action, okay, only a global action, then it will send n prime to all agents that can apply an action in n prime. Okay? So it generated a new node using a global action, and it basically sends that to any agent that has an action whose preconditions are satisfied in n prime. The message will contain the G and H values and the grading action. That's standard. So let's illustrate this with an example. So I'll start with an abstract example. What you see here is the actions of two agents. The yellow actions are local actions. Okay? And the red actions are global actions. You can see here the, I don't know if you know the SAS formalism, but it's preconditions, prevail conditions, and effect. So basically this action, A3, requires that V2 will be 0, and the effect is that V2 will be 1. This is a multi-value variable formulation of planning. This red action requires that V1 will be 2, V2 will be 2, and then V1 changes to 3. This is I don't know if you've heard this term, prevail condition is a precondition that is not affected by the action. So you need V2 to be 2 in order to apply the action, but the action doesn't actually impact V2. Anyway, the point is that this A5 and A6 here, or A8 here, affect the same variable, V1. Okay? So V1 appears, especially in particular the value V1 equals 3 appears in the description of both of these actions. That makes them global action. All the other actions are local. What you see here is the search space you would obtain if you were to expand this using regular A star. What you see here are the individual search spaces of each of the agents. So if this is the initial state 0, 0, 0, then these are the 3 actions applicable. This is what you get in A star. 2 of the actions belong to agent 1, one of them belongs to agent 2. And now we gradually expand this. Of course, this is I'm showing the entire search space. And you see, we gradually expand this. You see that this agent, for instance, is not doing anything once it got to this state because there's no action that can apply to to this state. And this action is continuing to do the work. This is what you have in the centralized case. And this action now agent now generated a state using the global action A5. The preconditions, and in this state here, the preconditions of an action of agent 2 are satisfied. So it sends this to agent 2, who can now continue to perform the expansion and eventually gets to closure. Notice in this example, you have a sense that the search spaces are much smaller for the single agent case. Which is not clear why, but it seems like we're doing the same thing. So I'll talk about this, but this is a general idea. Here's an example, thanks to Shlomi, in the logistics domain. So we have this truck here and the package here. The goal is the package to be at C. The truck cannot cross this dashed edge with a package on it. It can only cross it without a package on it. So here's the search. So we start with agent 1. Basically, it can load the package. It can drive from 1 to A. It can then unload the package here. Then, at this point, the precondition, at this state, agent 2 can apply an action. So it sends the state to agent 2. Agent 2 will load the package to its own truck, and then it will move to 4, and then it will move to B, and then it will unload the package at B. At this point, at this state, agent 2 can apply an action. So it sends, there is an action whose frequent, well, okay, cheating a little bit, but okay. So this state is sent to agent 1 because it can apply action in this state. And agent 1 will drive from here. Basically, it will reach this location. So these are all the driving action. And finally, it reached this location now. Now it can load the package, and now it can basically move it until to the destination. Okay. So the idea is that agent expand using their own actions. If the state they generated is relevant to another agent, they send it to another agent. And for that agent, that state is just entered into its open list, and it will use it like any other state in the market. Very, very simple algorithm. Questions on the algorithm? Here are some very old results. What I want to look at here, so this is A star. This is the running time for A star. This is the running time for multi-agent distributed A star. And this is the efficiency. So we have here, and you see here also the number of agents. Multi-agent distributed A star has an advantage because we have more hardware. We have here, for 3 agents solving the problem. So we're naturally enjoying the effect of distribution of the work. But you know, in distributed systems, if you take a problem and you distribute it to a number of agents, the best that you can expect is that the running time will be reduced by a factor of the number of agents. If all the work is divided exactly among all the agents, no agent does any extra work, no one has to do some extra work because of the distribution, then the best you can expect is that the running time will be the original running time divided by the number of agents. The efficiency factor is how close you are to that. And in any reasonable distributed algorithm where you didn't actually change the algorithm, the efficiency can never be more than 1. 1 is the case where you get the running time to be exactly the original running time divided by the number of agents. And what you see here is that in some cases you get efficiency higher than 1. And that basically tells you that the search here is not the same. There is something beyond just distributing the work. So what is it? So this is known as superlinear speedup. Superlinear speedup implies something beyond simple distribution is taking place. So the extra power we get here is from pruning. And where do we get the pruning from? So This algorithm has a pruning effect because of the fact that we do not send all states relevant to other agents to them, but only states that were performed after a global action. Okay? And the reason we can do this is because we can always rearrange any plan so that it has the following property. There's always a permutation of an optimal plan that is a legal plan that satisfies the following condition. Where is the condition set? There are no two adjacent local actions that belong to two different agents. Or, put differently, following a local action of an agent, only that agent can act. So look at this sequence here. You see here local action of 1 followed by local action of 2. But what does it mean for an action to be local to 1? It means it doesn't impact anything that is private or non-private, and anything that's private to another agent, and anything that is not private, sorry. Anything that is local to another agent, or anything that is global to another agent. So this means these actions do not interact. I can switch them around, and it will have no effect on the plan. So I can basically continue to switch these, I can push this action forward, forward, forward. When will it stop? When it reaches an action of the same agent. Because only this agent 1 it can be impacted by an action that is local to it. So I can push it all and get it into this form. So basically, any plan can be permuted to have this property where, following a local action of an agent, only actions by the same agent occur. And this gives us a certain pruning effect that we see, that you also see visibly in this case. You see many fewer search states in here. It's not always the case, but in some cases you can really benefit from this.
Question. Is this in a special case where people in a normal heuristic search call commutativity pruning? That if you have many actions that can commute in order, to achieve some effects, then you do a prior order, and then you prune every path where the actions.
Closely related. To be honest, I don't remember exactly the. I need to remember exactly what's the. It is a form of commutativity, but. You know, I've talked with Malte, who's worked a lot about all these partial order reductions. This type of pruning doesn't seem to nicely fall within the existing ones. It has some differences, but honestly, I don't remember exactly the precise distinction. Yes?
The H values the agents are computing locally, is that the global H value taking into account the whole problem, or some sort of local?
So as long as we don't care about privacy, it would be the heuristic value based on the entire information. When we look at privacy, then they will be computing a privacy-preserving heuristic, which could be different for different. So the values could be different to different agents, and it will be less informed because they have less information about the domain. If you care, for instance, about optimality, you can still make it invisible. And there's been quite a lot of work on coming up with good heuristics that maintain privacy. Okay, so a natural question to ask now is, can we apply this to single agent planning? And if we want to do it the fair way, let's say in single agent planning, we want to do it automatically in a domain-independent way, then we need to somehow come with an automated decomposition method. So here's an idea. There hasn't been much work on this, but here's an idea of how to do a decomposition. We can look at the graph. We can look at the graph of the actions and try to use a clustering algorithm to cluster the actions into sets. So what graph should we look at? The natural graph is what we call the action-interaction graph. You've seen it before. You've seen the agent-interaction graph. Think of each action as an agent, and two actions interact if they share some variable in their description, some proposition, primitive proposition in the description, actually. Okay? Now, these algorithms not only need, so when you cluster, you need to give some objective function that you're trying to optimize, And we have to think about what would be a natural objective function here when we try to cluster actions. So, and we want to have as few global actions as possible because it's the local actions that commute, right, with everything. So here's the solution, single agent on global actions. Everything is local. Not local. Okay, no decomposition. Okay? Let's take the other extreme. Each action could be an agent, and then we have many agents, but then it probably is going to be the case that all of the actions are global, because unless an action, if an action doesn't impact anything that any other action impacts, it's not too natural in a natural planning. So we can try to balance both. Here's a way to try to balance both. Look at a certain, here's a measure for the goodness of a partition. This measure basically looks at the portion of pairs of actions that satisfy this property, that they can basically commute. That A is an action private to agent I, and A prime isn't an action of agent I. Any two actions with this property can commute. So the more the proportion of the more pairs of actions have these properties, the more permutations we have, and the more pruning effect that we're going to have. Okay? So you can use some algorithms to do that. Interestingly, if you look at some natural multi-agent domains, like the logistics domain, these algorithms don't give you the natural partitioning. Often what they do is they group a few natural agents together into one cluster. And you can also use this to partition out domains where there is no apparent multi-agent structure, although usually that doesn't buy you too much. And here's something that shows basically that this measure that I've described is correlated reasonably well with performance. What you see here is the value of this measure. As we move to the right, there are more pairs of actions that will commute. So your basically abstraction, your choice of the actions leads to more actions that can commute. And here is the running time. As you see, that a very clear trend. As the number rises, most problems that fall into this will be solved faster. Okay. So, this is an intermediate summary of what we've seen so far. We looked at the language for describing multi-agent planning problem called multi-agent strips, which is strips with actions associated with agents, or basically strips with a set of action partitioned. The agent for us could be real or abstraction, generated manually or automatically. The first method tells us to solve a certain global coordination problem first, and then fill in the local details. When the global coordination problem is based on a domain which is loosely coupled, and not too many actions are required by each agent for the coordination, then we get an efficient algorithm. The second method is very simple way of distributing forward search. Well, as I said, there are new results that may make this not as true as it was before. It's much more efficient in practice. And you can combine the two ideas. So actually the new results combine ideas from forward search and from global solution and then local solution. Okay, and now I'm going to try to gradually introduce a more complex issue. The first is privacy, because this is often the justification given for why we care about the type of distributed algorithms that people look into in the multi-agent planning community. Because if privacy is not an issue, then notice that the way that I've defined distributed forward search is somehow respects the agent structure. Why? Because an agent only applies its own action. If all you care about is just efficiency, task distribution, no one says that this is the best way to distribute a task. But if what you care about is also privacy, and you want agents to not expose much information, then it makes a lot of sense for the agents to apply their own action. This way I don't have to describe to other agents too much about my actions and my local variables and so forth. Otherwise, if I do some arbitrary distribution, then I have to tell arbitrary agents arbitrary information, and I probably don't want to do that. So the idea behind so first of all, we have to somehow formalize privacy, and then we have to try to see if we can preserve privacy in some way. And we would expect that when we add this additional requirement for preserving privacy, then we're probably going to get some performance loss. It probably will come at some cost. Okay. So first of all, modeling privacy in multi-agent scripts. We're going to make it very simple, because originally this is what it was. Global was called public, and local was called private. Okay? So this makes a lot of sense. If we force global variables to be private, remember a global variable is one that appears in the description of multiple agents' actions. So suppose that, for instance, the location of the London truck, okay? No, sorry, that's the location of the package, okay? If I make this private, then some agents, and I don't want to expose this information, then some agents that need this information in order to carry out their action won't be able to carry out the action. They won't know the value of a variable as a precondition for their action. It looks like in such cases we're not going to be able to plan. So it makes a lot of sense to think of all the global variables as public. Now I will say there are more refined notions of privacy in private and public. I'm not going to discuss them, but you can do a little better than what I'm talking about. But this is the essence. Okay? So if we force global variables to be private, we are probably not going to be able to generate some plans. Whereas if we force some local variables to be public, so say my location. If I don't care that you know about my location, fine. It just makes everything easier. So it makes sense to assume that that all the global are public and all the local are private. And if you want to make some local public, fine, you can make them public. It makes things easier. But this is like a baseline, because you cannot make something global to be private without giving you some problems in finding plans in certain cases. And why not try to go for the maximum privacy? Okay, so we're going to think of global as public, local, private. And the idea is that I don't want to expose my private variables to other people. They could be my location, my inventory level, things like that. And I don't want to expose my private action. I don't want you to know what exactly I do in order to produce some goods that I sell to you. And all you need to know is that I can give you that good. Now, it seems that an area like privacy needs to come to, if you claim that you have an algorithm that preserves privacy, we first have to say what it means to preserve privacy, and we need some formal guarantees. And actually, this is a major open issue. This issue is, although there's lots of work in the past few years on privacy-preserving algorithms, privacy-preserving heuristics, the formal aspect of this is not worked out well enough, at least in my opinion. Existing methods basically guarantees that they will not expose information explicitly. Okay? So, for instance, I may send you in distributed forward search, I will send you the state with my local variables encrypted. And so you don't know my local variable. The question is this good enough? Okay? So, I send you all the local information is encrypted by me, you cannot decrypt it. Is it good enough? If your baseline is the area of secure multi-party computation, which is the area of cryptography that deals with secure computation, with privacy-preserving computation, then this is what they usually require. They require that an agent should not be able to deduce from information it is exposed to during the run of the algorithm anything it cannot deduce from its input and the solution plan. So in secure multi-party computation, they're concerned with the issue of jointly computing a function. You can think of the function that we're jointly computing and the function that outputs an optimal plan or some plan. The input would be the domain, of the different variables. And what I ideally we'd like is that everything that every agent can only be able to deduce after the algorithm, anything that it would have been able to deduce from its own part of the input, that is its own domain description, its own private actions, and the final solution plan. Now notice that in distributed forward search, for instance, an agent gets much more information during the run of the algorithm. It gets many states. It gets lots of messages with states. It's not clear that it cannot deduce something from it. So the idea that if you want a secure multi-party computation, private information should not be exposed even implicitly. It's not enough that I encrypt my information. You shouldn't be able even to deduce anything beyond. So here's a simple example, okay? This is an example we've seen before. Now, the amount of fuel of this truck is part of its private state, okay? Now, if you look at forward search here, it can read, so when does this truck send a state to an agent? When does the blue truck send its state to the red agent? When it basically reaches a location that is shared by two of them, reachable by two of them. But there are two ways to reach A. It can either go directly to A, or it can go in this way, okay? So if you look at distributed forward search, this implies that agent 2 will receive two states that are identical as far as the global facts, okay, but are different as far as the local facts. So even if they're encrypted, they're going to be encrypted in a different way, and it's going to get it twice, okay? So what can that agent learn from it? It can learn it can learn something. I'm not claiming that it learns exactly what the local state of the other agent is, but for instance, it can learn that it has two different ways to get to A. That means that it has at least two different local locations, and that its fuel level is greater than 1. Okay? So the point is that although explicitly we haven't sent any information about the private state, you will implicitly learn something about this. Now, is this something that you learn terrible? I don't know, but if you want formal guarantees, you need to take this into account. You need to say, you ideally need to say what it is that you can learn from the algorithm. So there are initial attempts to formalize this. I find them still unsatisfactory. I'll just mention two notions. We say that a private algorithm is weakly private if private information is not explicitly communicated. So the example of encryption is that, and that's basically the guarantee that most current algorithms provide. It's a very weak guarantee. Although again, we have no way, we have no way of saying how weak it is, okay? Because it's not clear exactly what one can deduce from the algorithm. The other extreme is what you see in secure multi-agent computation. A strongly private algorithm, no information can be deduced from the information exchange, it can be deduced from the input and the public part of the solution part. It's very desirable because it's a very strong requirement. There is one algorithm that does this in very restricted setting. If you want to, theoretically, you could actually use method from secure multi-party computation to provide this guarantee, but this is hopeless. Basically, in secure multi-party computation, you build a Boolean circuit that describes the function that you trying to compute, and then you can use various secure operations to compute the different steps in this Boolean circuit. And if you try to build a Boolean circuit of the problem of the function that computes the planning problem from input, that's not something realizable right now. And there's some attempts to provide some new ideas. For instance, cardinality privacy. That means that I will realize that you have a certain private variable, but I will not know how many values that variable has. For instance, you may have various private locations, but I don't know how many. Or you may have a number of trucks, I don't know how many of them. There's also a notion of agent privacy, which says that agents are unaware of other agents that do not have shared constraints. So I think I have a slide. So remember this example. If we have an algorithm that preserves agent privacy, the green track will not be aware of the blue and the purple track. The red track will not be aware of the purple track, and so forth. The blue track will not, the purple track will not be aware of the red track and the green track because they have no shared propositions with each other. This is the notion that comes from distributed CCP algorithm. I don't need the animation. I left it there. I thought I moved it. Okay. So how can we, let's look at the algorithm to describe and see how we can maintain weak privacy. As I said, this is what we have right now in most algorithms. So let's look at the CSP approach. And if you think about it, it's already weakly private. Why is that? Because if you look at the constraint problem, the global constraint problem that we want to solve, it has only global information in it. No private information is involved in it. And then each agent does a private part on its own. So it doesn't have to send this to anyone. So it's already preserving weak privacy. Note that it's not preserving strong privacy. Why? Because we generate certain global solution, okay? And then we let each agent try to fill in the details. And then I say, sorry, I cannot fill in the details. I cannot solve the local planning problem in this particular solution. You may be able to learn something about my capabilities from this. Okay? Forward search. Again, forward search is easy to adapt into weak privacy because agents only apply their own actions. So when I get a state, all I care about that state is my local state in that state and the global state, and the global part of the state. Okay? So, as far as I'm concerned, if all the other local states, the local state of all the other agents is encrypted, it doesn't affect me. I can still apply the operators because my operators do not affect their state, so I can simply leave the same value that I see. Okay? I get your encrypted state, I apply an action, it doesn't affect your encrypted state, I just keep that value around. Notice that we cannot send to each other information that doesn't include the encrypted private state. Because suppose I apply an action, I send you a state without my private part, and you apply an action and you send it back to me. If I did not originally send you my encrypted private state, I will not know what is my private state in the state that I get back from you. So I don't know what action I can actually apply. So I have to send you these encrypted private states so that when I get things back to me, I'll be able to know which action to apply. Okay, so that's weak privacy. We also have to make sure that the heuristics are privacy preserving, right? So a simple approach is an agent-computer heuristic estimate only based on what we call the public projection, which is what I mentioned before. It's a set of public action without their private preconditions. Okay? Then different agents will generate different heuristic estimates, which is not a problem to the algorithm. Could affect the efficiency but not the correctness. And this is a very weak heuristic, and there's been quite a few work on heuristic based on landmarks, privacy-preserving potential heuristics, stronger methods for projecting, and that are much more efficient than this, and this is an area of active research. Okay. So, this is about privacy. Agent interaction. I mentioned this initially in the list of things. So, for instance, we have two agents that there is a big box that can only be pushed if two agents push them. And maybe if one agent pushes it, he will hurt his back. So it's a bad idea for one agent to do that. Two agents cannot move into the same location. If one agent lifts the table, everything falls off the top. But if two agents lift the table, it remains. So as I mentioned initially, the key issue here is representing the interaction of the actions. So first of all, imagine that the interactions are always negative. It has to be defined clearly But it means that some combinations of actions are either ill-defined, so we're not sure what will be the effect, so we don't want to take them together, or they will do something bad that is always undesirable, like, say, breaking a glass. So, very simply, we can disallow one very simple option. Since the interactions are only negative, there are no positive interactions. We can simply disallow simultaneous actions and we're done. Okay? The problem with that is that there's no loss of generality. Everything you can solve with simultaneous actions you can solve without them in this case. But you obviously pay the price of not being able to run things concurrently and maybe do the plan, finish the plan more quickly. The other option is to specify constraint on simultaneous action. There's been some work on this. Can be achieved, for instance, by limiting the number of actions that mention an object. So if at most 3 cars can be on a bridge, then we can associate a certain constraint with the bridge object that will ensure that will basically tell us that no more than 3 agents can manipulate can apply an action that involves the bridge. Again, there's a short bibliography in the end of my slides. If any of these the topics I'm going over now, I'm going to just give you a glimpse of. So if you want more information, you can see you can see references there. Okay, negative interactions are reasonably easy to deal with. But what about general interactions? So if there are general interactions, it means that some of the combination of actions may have interesting effects that may be useful for us, and some could have negative impact. So we could model them explicitly. This is notion of joint action. If you have a multi-agent system, the natural notion is not of a single agent action, a multi-agent system in which agent can act simultaneously. The natural notion is what's known as a joint action. A joint action basically specifies what everyone does at this time and tells us what is the impact of this combination of single agent action. The problem is that if you have n agents, k actions each, then you have an exponential number of joint actions. So you have a serious representation issue. So efficient representations have to exploit independence in some way. And one way of doing this, basically exploiting the independence, is rather than explicitly talk about joint action, still model single agent action, but makes the effects conditional on concurrent action. These are just 2 options. There may be others that I haven't seen. So here's an example that illustrates this. So we have this, here's a joint action by the 2 agents of pushing a big box. Okay, so it has 2 agent parameters, the box, the initial location, and the goal location of the box and the agent. Preconditions are the agent of the location, the box and location, the box is big, and the effect is that the agent and the box are at the new location. Okay? So it's a joint action, it describes everything about both of the agents. You can also try to describe single agent actions and make them conditional on, not as in regular conditional effects, what happened before the action was executed, but on what is happening simultaneously with the action. So, here we see the example. So notice this is only describing what is happening to agent 1. It's a single it's describing things with respect to a single agent. Sorry. So, the precondition with respect to that agent only in the box. This is the Allen field, which says, is there an action that has to occur concurrently? Is there a concurrency constraint? So, in general, there's no concurrency constraint for pushing the box. Okay? Now look at the effects. The effects are conditional effects, and the conditional effects too have a concurrency condition. So when this holds, the box is not big, there's no required on concurrent action. And then the effect is, sorry, should have used semicolons here. This is a precondition, concurrency condition, and these are the effects. So the box is basically changed its location. And also the agent should change, sorry, there's a mistake inside. The agent also has to change. But when the box is big, this is a concurrent action condition. There has to be another agent that performs the same type of push box action with the same initial and goal location, okay, and the same box. That agent has to be different than our agent, performing agent. In that case, the box will move, okay? Notice that the effects here are only with respect to agent, the first agent. The effects to the other agent pushing will come through its own copy of the action, where agent, instead of agent, will have agent prime. Okay? So this is basically describing the joint action, and this is a modified way of describing single agent action, which makes sense if usually there are no interactions. So if there are few interactions, you'll have a few cases of conditions, and this will be an economical way of representing things. Yes?
But how do you make sure that these actions happen at the same time if they need to be converted?
So when you plan, okay, when you plan for it, you have to have a planning algorithm that is able to use this description. That planning algorithm will output a certain, how it does, I'm not going to talk about, there are ways of doing this. When it outputs a solution, the solution will be basically a sequence of individual actions, some of which may be in parallel. And then the question is to verify whether this solution has the right effect. So you need to be able to say, for instance, progress a state forward given a certain set of actions. So if I am giving two actions, simultaneous actions that have this push box, with the same box, same initial location, and same goal location, but two different agents, and based on the specification, I know that the effect is fine, it's satisfied, because when I look at the plan, then in my plan this is satisfied. Okay? How we generate it is a different question. But this is what we need to be able to do, is to verify in this case from the description. Does this address your question? Okay. So I'll just mention a few things about the algorithms. So of course the algorithm that you use will depend on the choice of representation. If you do the CSP approach, for instance, you can do the CSP approach with this. You just need to have more involved constraints that take into account the concurrent actions. Also, if you do distributed forward search, what you need to do is basically when I apply an action, I send you a state, but you can decide when you get the state whether you want to apply another action at the same time, or you want to not apply another action at the same time, just apply another action later. And this way you can develop the search space, sometimes applying concurrent actions, sometimes applying no concurrent action. This makes sense with the second representation, this representation. There's some subtle issues about conditional effects and so forth. I'm not going to go into it. Okay. So now we come to the issue of selfish agents. A selfish agent is one that maximizes its own utility. It will not perform computation or take action if they lower their utility. It will only participate in plans if it has some positive utility. You can make that even stricter. It may lie about the nature and about the cost of its action if it's beneficial to it. We're going to assume that the utility of the agent is basically some payment it receives. You can think of the payment here as payment given to it, or the value of the goals that it achieves, minus the cost of its actions. Okay? So this cost j of pi is the cost of j's action, or is it I? Cost I of pi is the cost of i's action in plan pi. Okay, pi is a plan, and p is called the payment scheme, which is basically how much each agent gets. Again, it could be the value of the goals to each of the agents, and it could be some actual payment that we'll see soon. So what's the problem? The problem is to get a group of agents that are selfish. They have private information, like in the example we've seen, their own private actions, and also the cost of their actions. We want to get them to perform together. Let's first look at the problem. We're trying to get them to do a cost optimal plan. And the key ideas here is to combine distributed planning with ideas from game theory. So there is a mechanism called Vickers-Clark rules, which is used, originally it was used in auction, but it's used in many other settings. If you combine it with distributed planning, you can get privacy-preserving distributed mechanism that has this property that is called ex post faithful. What is ex post faithful? We say that an algorithm is ex post faithful if it is in the best interest of every agent to truthfully follow all aspects of the algorithm, in our case, in revealing the information, passing the messages correctly, doing the right computation, regardless of other agent private information, given that all other agents follow the algorithm. So in a nutshell, I have no incentive to diverge from the algorithm and tell you untruthful information, assuming you do the same. So if I unilaterally cheat, I will gain nothing by it. Okay? I may not lose. It's possible that I will not lose, but I will not gain anything by it. So let's see how we can do this. So first of all, what's Vickers-Clark rules? How many people know this? Okay, most of them. So this is a general mechanism. I'll describe this in a little general terms, and then we'll move to planning. So it's a general mechanism originally for auctions. So agents report private information to a trusted center. We are aware of the fact that they can cheat. They may, the private information, say in auctions, is how valuable the auction good is to the agent. And as you probably know, if you've gone to an auction, usually you don't tell the right value, the true value, right? You try to say something lower. So we don't care about this. They can say whatever they want. The center computes a solution, a payment to each agent. Now the point is that the payments are computed by solving what are known as the marginal problems. So imagine we're all having an auction, and then you take me out, and you do the same auction, but without me. That is the marginal problem obtained by marginalizing me out, okay, taking me out. So if I'm out of the problem, then I don't influence the solution, right? So that's an important part of this marginal problem. And what the mechanism guarantees is that efficient, the first one is efficient. It will output a good solution. Technically, it will output a solution that maximizes the sum of utility of all the participating agents. And it's strategy proof. What does that mean? It means that truth-telling is weakly dominant strategy. This means you gain nothing by lying. You might want to give a lower cost than your real cost, but it's not going to buy you anything. So you might as well tell the truth. So how do we apply to planning? First, let's use the centralized BCG mechanism. As you notice, we assume here a trusted center to whom we give all the information. And this center will compute the solution. So let's start with this. So agents report private action and their cost to the center. The center computes an optimal solution to the original planning problem. No, this is pi star. This is optimal solution to the original problem. Then it computes an optimal solution to each marginal problem. This is a problem without each one of the agents. So pi minus I is a problem where we exclude agent I. It's the agent I actions are not taken into account. Then each agent receives the following payment. So this is a payment that agent I receives. So what does this say? This is the sum over all other agents of the cost to the other agent in the plan without I minus the cost to the other agent in the original plan. So if you think about each term in the sum is basically the benefit agent J has from agent I being in the plan. Because if agent I is excluded in the plan, you will have to pay this cost, which is likely to be higher than the cost that it pays when agent I is in the plan, because agent I is probably going to perform some of the actions. So this is a benefit to agent J. Each element in the sum is a benefit to agent J of agent I being in the plan. So here's an example to illustrate these ideas. So let's think about the logistics domain. We have three agents, A1, A2, A3. two packages, package 1, package 2, two locations left and right. All the agents, the packages are initially at the left. Package destination is the right. And we allow at most one package per truck. Okay? So a truck per AM. The agents are the truck, basically, are the trucks. Here is the cost of the actions. So loading and unloading for agent 1 and package 1 is 1. For agent 2 and agent 3 and package 1 it's 2. For package 2, agent 1 and agent 3 pay 2 to load and it costs them 2 to load and 2 to unload. And agent 2, it costs only 1 to load and 1 to unload. Okay? Move costs 1 to all of the agents. Okay, what is the optimal solution? The optimal solution would have agent 1 load package 1 and move to the other location and unload it. That would be cost of 3 to agent 1. And similarly for agent 2 who will handle package 2. So the total cost of the plan is 6, right? Agent 1 loads 1, moves 1, unloads 1. Agent 2 loads 1, moves 1, unloads 1. Okay, now what happens when we look at the marginal problem? This is the problem without agent A1. Okay? The optimal solution to each of the marginal problems without A1 and without A2 is A. Because if A1 is not part of the solution, then instead of this cost, we'll have to use agent 3, who will pay a cost of 2 to load and a cost of 2 to unload. So we'll have an extra 2 here for the cost. Now let's look at the cost for individual agents. So notice that if we exclude agent 2, okay, agent 1 is not impacted. Agent 1 will still do the load, move, unload of package 1. So the cost to agent 1 is 3, exactly as in the original plan, optimal plan. Similarly for agent 2, if we exclude agent 1, agent 2 will still be in charge of this package 2 and will do the same work. Okay? So in the optimal plan, so these agents are not impacted. Agent 2 is not impacted by moving, agent 1 is not impacted by removing agent 2. Agent 2 is not impacted by removing agent 1. What about agent 3? Agent 3 originally really does nothing in the original plan, so the cost of the original plan is 0. If agents are removed, either 2 or 1, it will have to load and unload and move, so the cost to him would be 5. So what is the payment that we have to pay? So if we exclude the payment, if we exclude 1, and if we exclude 2, in both cases, so if we think about, say, agent 1, we've seen that agent 1 is not impacted by excluding agent 2, and is not impacted by excluding agent 3. So the payment for that agent will be, the payment to agent 1 and to agent 2 is 5. Why is it 5? If we exclude agent 1, then agent 2 is not impacted, but agent 3 is impacted. So the cost to agent 3 increases by 5. So the term here about agent 3 will be 5. The term for agent 2 will be 0. So it will be 0 plus 5. It's similar if we exclude agent 2. If we exclude agent 2, agent 1 is not impacted. So if we do this, the cost in the excluded problem minus the cost in the regular problem is 0. But if you look at agent 3 again, he will have to pay 5 more when agent 2 is excluded. So 5 is a payment that agent 1 and agent 2 should get. What payment should agent 3 get? If we exclude agent 3, then no benefit. We have here 0 for agent 1. We have here 0 for agent 2 because excluding agent 3 doesn't impact their task. So agent 3 should get a payment of 0. Is the example clear? Question? Okay. So this is basically the idea behind the VCG, the combination of VCG and planning. And you can now get a, okay, so basically this is how you would do a centralized solution of a planning problem that has all these properties that I mentioned before. That there's no incentive to lie, you get an optimal solution, and so on. And if you want to distribute it, then you have a problem because the VCG mechanism requires a centralized trusted center. And if you want to preserve privacy and still maintain the guarantees of VCG, you can still do something. And what can you do? You will let the agents compute the solutions to all of these problems and all the payments in a distributed manner. This means basically we have all, so let's go back to this slide. We have all of these problems to solve, all of these marginal problems to solve as well as the original problem. We'll just use distributed forward search in the regular way to solve all these problems. We'll solve each of them using distributed forward search. If we maintain privacy in distributed forward search, we can maintain it here. And we can also let all the agents make the computations. If you look at the, I'll show it in the next slide. You can look at the computation, you can see that the payment to agent I is not influenced by agent I's action. So basically, okay, let me take a step back. So the idea again, we want to solve this problem in a distributed way. We could solve each of the distributed problems, but we have to be careful. If we have now a distributed mechanism, we have to make sure that the agent do not manipulate this mechanism. In this example, what they could do is lie about their costs. And because of the VCG mechanism, that's not useful. Everything else was done by the center. But if we allow them to do things distributedly, then they can cheat during the run of the algorithm. For instance, an agent may decide not to send a state that it generated to some other agent. Okay? So they can cheat in the running of the protocol. So we have to make sure that they don't. Well, we can use distributed, selfish multi-agent distributed A star. We run multi-agent distributed A star on the original problem to find the original solution. And then we run it on each of the marginal problems. Yeah? When we run it on the marginal problem, the agent that's marginalized and has the incentive to lie and change what's happening there has no incentive to do it it cannot impact it in the marginal problem. And then we have the computation of the cost. We have to compute the cost also that has to be paid. And if you manipulate this equation, you see that eventually the cost that agent I has to pay is its cost in the problem where he's excluded. So he cannot impact its computation, minus this sum of costs that don't involve him. So agent I is not involved in the computation of its own payment, so he cannot influence it. So basically, this is the idea behind having a selfish version of multi-agent distributed A star. In fact, you don't have to compute these problems separately. So you have to compute here a number of planning. We have to solve a number of problems that is the number of agent plus one. The original planning problem and one for each agent being excluded. But the search spaces are really, most of them are shared. So you can actually solve one big planning problem that solves all of these problems together. And okay, here are some results of this algorithm. You see what you see here. This is A star set. Okay, this is when you do the centralized VCG. So of course, the centralized VCG, there is some additional cost, but it's minor. This is what happens when you try to do the distributed way. And this is with some optimization where I mentioned that you can think of it as a single search space. And you can definitely see that there is a cost to selfishness. Okay? And if you want to solve a problem where agents are selfish, at least with current algorithms, you can solve interesting problems, but you can see that the running times stay here. Okay, 1 versus 67, 11 versus 3, 7, 12 versus 40. There's a performance loss here. Okay. There's some subtle points which I'm going to skip. I'm also Yeah, I'll just mention a few words about planning games also. We've assumed what I've done just now is that an agent will participate in any solution in which it has positive utility. But, you know, we're in Euro time, right? And also Copa America. And do you think that Lionel Messi will agree to play in any team in which it has some positive utility for playing in the team? So by just paying $1 a game, will he play? No, he has other options, right? And do you think that we should also, in a reasonable situation, it's likely that we'll pay Messi and say, you know, without offending anyone, David Silva, the same salary? Probably not, okay? Agents acting in the world have alternatives. It's not that, you know, I come to them with a proposal for a plan, and I show them that I promise them that thanks to BCG you're going to get positive utility, blah, 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 and they take it. They have alternatives, you know, they can join one group or another group. They can, you know, if you think about the example of contractors building a house, you know, a certain, say, plumber can, you know, join out different groups of contractors to bid for, say, a project, right? And so it's not enough that we find a plan, we find a group of agents that will perform the plan, each with positive utility. We also have to make sure that the plan is, in the sense of game theory, stable. Right? There's a notion in what's known as coalitional game theory of stable coalitions. Coalition is stable if there is no incentive for agents within this coalition to form a different coalition. So again, the issues, what happens, the point that I want to get across beyond the specific detail, that when you look at multi-agent planning problems where you have selfish agents, then you have to take into account various ideas from game theory, and you have to use techniques from game theory, combine them with planning in order to solve the situation. So planning games is just one formalism that looks at this issue of how you form coalition, how you can generate a plan and a coalition that will be stable, so that the agents who are part of this plan will want to remain part of the coalition. And also, one of the things that you have to think about when you generate give such solutions, it's not enough that I tell you who does what. I also have to tell you who gets what part of the profit, right? Messi and David Silva are probably not going to get the same amount, even if both of them play 90 minutes. Okay? So, we'll skip ahead to uncertainty. Okay. So you had a lecture on uncertainty yesterday, and I assume many of you also know about it from your previous background. We have lots of aspects, different aspects of uncertainty in single agent planning. So you might have uncertainty about the effects of action, such as in Markov decision processes. You might have partial observability. You don't know what's the state of the world in which you start your you start acting from, as in deterministic POM-DPs, or you can have both of them, actions that are stochastic or non-deterministic, and uncertainty about the world, and you get POM-DPs. Okay? We have all of this in multi-agent systems. And when we think about these models, then we no longer talk about plans, because if I don't know what the effect of my action will be, it doesn't make sense that ahead of time I will decide what action to perform afterwards. I will be probably influenced by the state or the observation that I get when I perform the action. So we talk about policies, not about plans. So in distributed teams, you have all of these things, okay? But you have another important aspect. You have uncertainty that one agent has about the effect or the choice of the actions of other agents. So, and I'm especially thinking about systems in which you do need agents to act together simultaneously to achieve some goal, although this is relevant also in when that's not the case. Okay? So you may have a multi-agent system that has perfect information about the state of the world when you put the entire information of all the agents together. So you basically have something like an MDP when you look at the entire system. But during the run when you are actually executing the plan, each agent only has some piece of information, and that basically makes, even if the entire system has complete information, so from the perspective of the big system, we're in an MDP. From the perspective of the small agent, the component, we're in a situation similar to a POMDP, because it only has part of the information about the state. Okay? And each agent, when the algorithm is being executed, maybe offline you can think about everything and coordinate everything, but when the algorithm is being executed, all you can act upon is the information that you are exposed to, not the information that the entire system is exposed to. Unless, of course, you assume communication and everything is communicated, which reduces everything back to a single agent case. And in real life, in robotic system, you'll notice that the assumption that you can communicate everything is not really realistic. Okay. So if each agent has this POMDP perspective of the world, what's the problem? We know how to solve POMDPs. So let's see, what do we do to solve POMDPs? Again, I assume this was covered yesterday. So to solve a POMDP, we move into belief space, right? Instead of thinking about the state of the world, we think about distributions over states of the world. Or if you're looking at non-deterministic domain sets of possible states of the world, among which we cannot distinguish. So if we take the POMDP perspective, we say, okay, each agent will maintain a belief state over the states of the world, and we'll give them a policy that basically tells us what to do as a function of its belief state. That's the question, is that enough? Let's look at this simple example. Okay? We have these two agents in this very small grid. In each location in the grid there is a box. The agents don't know whether the boxes are inside the grid or outside. Basically, they can push the box outside of the grid, and their goal is to have all the boxes pushed outside the grid. What they can do is they can move right and left. They can observe whether the box is in or out in their current location, and they can push the box. Now, the small boxes, one agent is sufficient to push, but the big box requires both agents will push it in order to take it out of the grid. And if only one agent pushes it, it will hurt its back. So the uncertainty, initially the agents know that both of them are located in the respective states, but they don't know where are the boxes. Are they in the grid or outside the grid? So the agent, the thing is to notice that not only in order to solve this problem, we have to deal with uncertainty and partial information because we don't know where the boxes are. We have to observe if the box is in the grid or outside the grid. But when we're in the central location here, okay, the agent doesn't know whether the other agent will be pushing the box as well. So not only does the agent not know what the state of the world is, it doesn't know what the other agent will be doing. And that's very important to it because it doesn't want to hurt its back, right? So what kind of notion of belief state will we have in this case? So suppose that we want to assign an agent a policy that maps its belief state to an action. In a distributed team, an agent's choice of action has to depend not only on the real world, but on what the other agents will do. As I mentioned, each agent needs to know, will the other agent be pushing this box if it's in this location? And what influences what the other agent will do? Its own beliefs. So I need to do if you will be pushing the box, and whether you will be pushing the box depends on what you believe. Okay, so this means that agents not only need to model their uncertainty about the world, they also have to model their uncertainty about the beliefs of other agents about the world. Okay, so what does it mean to model? What should my belief about the other agent include? So agent 1 has to take into account what agent 2 will do, right? So that depends on agent 2's belief state. But agent 2 also has to take into account what agent 1 will do. And that depends on agent 1's belief state. So agent 1 has to model agent 2's beliefs about agent 1's beliefs. Similarly, agent 2 has to model agent 1's belief about agent 2's belief. So agent 1 has to model agent 2's beliefs about agent 1's beliefs about agent 2's beliefs. And so forth. Okay? Rather confusing, right? So how can we handle this infinite chain of belief? It seems that we have to model this infinite chain of beliefs. So here in our example, just to make it clear, agent 1 will need to push if it believes, it will push here, if it's here, agent 1 will push if it believes that agent 2 will push. Agent 2 will push if it believes that agent 1 will push. Okay? So agent 1 will push if it believes that agent 2 believes that agent 1 will push. And so forth. Okay? So how can we represent this? So one thing that people have done is simply to approximate it. Say, okay, we're not going to get into this infinite chain of beliefs. We'll just cut it at some level. Okay? We'll simply model agent 1 beliefs about agent 2 beliefs about its location and that of the blocks, but not agent 2's beliefs of agent 1. This is clearly an approximation done for computational reasons to have a more succinct representation of the belief state, and it can lead to problems. The other option is to maintain a full semantic model of the beliefs of the agent. This is known as the Kirkus structure. How many people know Kirkus structure? A few, very few, okay. If you have such a Kirkus structure, you can deduce everything. I can answer any query about any chain of beliefs about the agents. Problem is, I'll show you what a Kirkus structure is, because it's a very fundamental notion, but problem is it's not very scalable, because it requires an explicit representation of the states. So you need a model that explicitly represents all the states and some relationship between them. Problem. So what's a Kirkus structure? It's a graph whose nodes are possible states of the world, and an indistinguishability relation for each agent. Okay? The indistinguishability relation basically partitions the set of states into those that the agent cannot distinguish. Given this structure, we can deduce any nested beliefs that we want. So here's the example. So here's our example. Initially, these are the 8 possible worlds that each of the agents, these are the 8 worlds that each of the agents considers possible. And the agent initially have no way of distinguishing them. They've made no observation. They're starting with all of these as possible state of the world. And you see the different boxes in either in or out. Okay, so I don't know how clear it is. And this is what happens after the agent of both made an observation action. So each agent is observing. They're both, one is in this cell, 2 is in this cell. They're both making an observation. And they've made the observation out. So agent 1 noticed that the box is out, and agent 2 noticed that the box is in. So as far as the possible worlds for agent 1, look at the solid blue rectangle, right? Agent 1 observed that the box is out. So the solid blue, the states with solid blue rectangle, this one, this one, this one, and this one, are the possible states world for that agent, and it cannot distinguish between the 4 of them. Okay? I also marked with the dotted blue line the other 4 worlds, and had the agent observed in, these would be the 4 worlds it cannot distinguish between. Okay? Okay, all of the ones that are similar. You see that also the red, the solid red line is the indistinguishability relation of agent 2. Agent 2 observed that the box is in. So all the worlds in which the box is in, this one, this one, this one, and this one, these are indistinguishable to the agent, and these are the currently possible worlds. And it observed out, it would be this one, this one, this one, and this one. Yes?
So are you assuming 100% accurate
Yes.
sensors?
I'm assuming perfect sensor. Things get more involved with uncertainty. If you want to assume noisy sensors, you have to move you have to use a probability distribution to describe your belief state. Things get even more complicated. Okay, so these are the world agent 1 beliefs are possible. So now notice that this world here is one of the worlds not a good example. Okay, so you notice this in my. So imagine that agent 1 believes this is the real state of the world. Okay? Imagine agent 1 believes this is the real state of the world. In that case, it basically assumes or believes that agent 2 believes these are the possible states of the world. Why? Because if this is the real state of the world, it knows that agent 2 has made an observation action, then agent 2 observed that this is the state of the box in its cell, and therefore, but agent 2 doesn't know about what's happening here, so it will consider all of these states possible. Okay? Now, so this is what we had before. The imagine agent 1 believes this is the possible state of the world. This is what it believes agent 2 believes are the possible states of the world. And it also believes that if agent 2, that in this state of the world, agent 2 will believe that these are the states that are possible to agent 1. Because if this is the state of the world, the box here is outside. So if in this state, agent 2 will believe that these states are possible for agent 1. You can go on and on with this. The point is that all I need to do is, if I have this information, this partitioning, given it, I can deduce all of these possible change, because I can tell you, if this is the state of the world, which states can agent 2 not distinguish between, and which are the states agent 2 cannot distinguish between this state and them. Okay, these are the states, and if this is the state of the world, which are the states agent 1 cannot distinguish for, and so forth. So in principle, I can look at any level of nesting of beliefs. Okay. Complex structure, but it gives you, in principle, you can say anything you want, and you can say anything about the beliefs given this structure. To pick up on your question on stochastic case, so if you move to the stochastic case, there's actually a construction that won Arsani a Nobel Prize in economics, which is known as Arsani type spaces. I'm not going to explain it, and to be honest, I don't know it too well, but it's basically an idea called type space, which basically associates a set of possible types, where a type basically tells you everything about the agent. And he showed that there's a universal type space, it's infinite, can be approximated by a finite structure, and that basically lets you, instead of talking about the belief state, you basically talk about the distribution over types. And if you tell me the distribution over types, I can compute everything. Not practical computation, but just good to know that it is. And finally, actually, this is not a different option. This ties in well with this crypto structure. I'll explain it in the next slide. The other thing we can think about is this idea of histories. So what's a history? It's the initial state plus a sequence of actions and observations that I've done so far. And this is basically what most people use for planning. So let's see the relationship. What are these histories? So from a history you can derive, if we have a history, again, a history is an initial state, a concrete initial, a concrete initial state, and a sequence of actions and observations by the entire system, okay? All of the agents. So if you have a history, you can derive the possible states of the world, and you can generate this full semantic notion, this Skripper structure. So given an initial state in a history, you can see what states are reachable, okay? You can see which states are indistinguishable to an agent based on its observations. So two states are indistinguishable given a history if they would lead to the same observations. Two states are indistinguishable to an agent if the histories in these that generate these two states are indistinguishable to the agent. Remember, the history is a sequence of all the action observation of all the agents. If among these observations, the agent itself only sees some of them, the others are done by the other agent. So if there are two histories in which the agent makes the same observation, it cannot distinguish between these histories, and therefore it cannot distinguish between the states that these histories lead to. And then, basically, if you have this, you can construct a full semantic notion. So I'll give you an example soon. Here, just a second. So, suppose we use this idea of histories to represent the set of possible histories to represent the different possibilities, and we now want to give agents a solution. What does the solution look like? The two options. One is a set of local policies. I give each agent a local policy that tells the agent what it should do as a function of its own observation only. Okay? That makes a lot of sense, but sometimes it's hard to compute. Another option is to give a joint policy. A joint policy tells the entire set of agents what they should do, okay, as a function of the entire history. But that's not something that's executable in general, because when I act, I don't act based on the entire history, I act only based on the part of the history that I've seen. So it has to satisfy, so it has to be, the joint policy has to take this into account. So let's look at an example. So we're looking at this example that I talked about before, and here are two local policies for the agent to solve this example. So for agent 1, observe whether the box is in or out. If it's in, push it up. Move right. Observe the box. If it's in, push it up, and you're done. And you have different, say, if you observe the box and it's out, then move right. Do nothing. Then observe the box. Then if it's in, push it up, and so on. And similarly, a policy for the other agent. Okay? Here is the joint policy. This is a joint policy. This is the joint action of the two agents, so they both observe the box. And then depending on what each of them sees, there is a branch. This is easier to generate. Why? Because it takes a certain central view of the system. And it's easier to transform this into a regular planning problem, because we're seeing things from the system perspective. But we have to be careful that this is executable. And this is why you have these knobs here. So notice that what you have to make sure is that if you look at two paths that are the same from the perspective of an agent, its own action would be the same. So for instance here, agent 1 observed out, and here it also observed out. So it has to be the case that in both cases here, the action is the same. This is still a continuation of the same history that is indistinguishable to the agent, except that this is the second action now. So agent 1 doesn't know if it's here or if it's here, because it doesn't know what the other agent observed. So it has to be the case that the action is the same in both cases. So you can use ideas from single agent planning to generate a plan for the entire system, thinking of it as centralized, but you have to maintain this constraint of executability so that the agent can actually execute this. Notice here what happens is, because of this seems like unlogical that there is a step here where the agent don't do anything. Why not just have them both observe the box now if they're here? The point is that they don't know that they're here. If agent 1 thinks that it's either here or here, agent 2 thinks that it's either here or here. And because of this knowledge, they have to take this no-op action here because they might be here with the other agent doing something, only after which they can do the observed box action. Okay. So we're almost at the end. So how do we plan for these problems? So most work has been on offline centralized planning. What does this mean? Generate a plan offline in a centralized fashion to be executed by the agent. Basically generate something like this offline. Then the agent can take this policy and execute it online. How can we do this? Well, given a joint policy, we can evaluate whether it reaches a goal. So, this is a joint policy. Okay, this is a joint policy. In all of them, we eventually succeed. All of the paths here, we eventually succeed in pushing all the boxes out. So this is the solution plan. So if you generate a joint policy that solves the plan in all branches and satisfies these conditions that the policy is executable, so that given similar local information, action has similar actions, then you've solved the problem. Okay. You can use forward search to do this. You can actually, in fact, compile the deterministic version of this problem into classical planning and solve it. Terrible compilation, but you can do that. If you're looking at a stochastic case, which is called decentralized MPP, similar algorithm exists. Again, I said this is a really big area, but almost all the work in decentralized MPP is also focused on this offline case. Compare, for instance, to contingent planning. If you're familiar with contingent planning, lots of work on online. And the reason is this great difficulty in the online case. Imagine what happens online. If you think, well, how does online planning work? Like in the replanning approaches work in classical planning. I generate a plan, but I don't take into account all the options. Otherwise, I might as well generate a complete plan offline, and that's the same cost. But the point is that thinking about all the options is not realistic. So I'm going to make some assumptions, and I'm going to solve the problem. So let's say initially we all have the same belief state, and I make some assumptions. We make the same assumption, and we solve the problem. Okay? Now we start executing the actions, and suddenly we get to something that was unexpected. One of our assumptions wasn't true. Now, it could be the case that I realized that one of our assumptions wasn't true because I've made an observation that contradicts the assumption. But you didn't make this observation. I've seen that the box is in the grid, whereas I thought it was outside the grid. I only observe it, you don't observe it. Now I need to modify my plan because my original plan was made under these assumptions. So now I have to plan again with my new belief state. I don't know what your belief state is because I don't know what you've observed. So what assumptions should I make? How should I revise my plan online? And you might, for all intents and purposes, you might have seen everything as expected and you're just carrying on the plan as usual. But I noticed something that is very important. I have to revise my part of the plan because it's no longer relevant. And now what about the coordination? So this is a great difficulty of online planning in multi-agent systems. And there's really not much work on it. There's some work in decentralized multi-P recently, but this is a really, really difficult question. How do you, because the offline methods are impractical. They do not scale up, even in single agent case. So the offline methods are, they can solve really small problems because you have to solve the entire, for all the scenarios. You want something practical, you need some online method that makes certain assumptions. How do you coordinate these assumptions? How do you make them and revise them appropriately when information is, when agents get new information which is different for different agents? So this is really difficult problem. Okay, so that's it. Let's summarize. So there's much interest in the past few years in this area of classical multi-agent systems. The DMAP workshop is held every year for the past few years, and this year I think there's a record number of papers. It's increasing all the time. There was a planning competition, distributed planning, privacy preserving planning competition last year. So it's a thriving area. And if you look at problems in this area, know the model you're looking at, understand your assumption. In the classical arena, there are two basic algorithms that are, there are also a number of other variants, but these are like the two best performing algorithms as far as I can tell, and that can be combined effectively. And of course, maybe something new, or maybe one of the other methods can be made to work. You know, we've seen this happening in planning all the time. A method seems to be the best, and then someone comes up with something else. Privacy is really important to motivate much of the use of these ideas. And uncertainty, as I just noted, leads to really complicated settings with great challenges, but very important. You know, in realistic setting, uncertainty is almost always there. There's really a lot of work, much room for work. So many models with significant computational challenges in each: interacting action, uncertainty, task allocation, and more. How do you do automated factoring or factor planning automatically? Privacy, which is really crucial for many of the algorithms. How do we do the analysis properly? Can we come up with algorithms with stronger privacy guarantees? Lots of applications, Internet of Things, multi-robot systems, supporting collaboration between commercial entities. And if you're interested in, this is like a short, very partial biography of, that is especially about the issues that I've discussed in this tutorial. It's a very interesting topic, and thank you. Any questions? General questions? Yes.
So, is this model of beliefs and necessities is related to epistemic planning?
Yes, exactly.
So,
Yes.
based on this work of Thomas Hollander and kind of...
Yes, so yeah, they did the work in, they've done the work in the classical area, and in the Decomposition people also do. They don't call it epistemic planning, but they have to represent beliefs of, beliefs and beliefs over beliefs and so forth, but yes.
Okay, so there is also a notion of public announcement where an agent, public announcements, so where an agent tells some public information and the other agents update their knowledge base accordingly.
So this is a way to solve this coordination problem, right?
Okay.
So what you could ask is, one way to approach this is to ask the following question. Suppose that my way of addressing this lack of coordination or mismatched information is to announce information that is relevant to other agents. You might want to ask the question, how do I minimize, for instance, the number of what you call public announcements, okay? While ensuring that agents are sufficiently coordinated. So there's really lots of different directions you can take this and go. Other questions? Okay.
I have a question.
Yes.
So what is your take? So some people are working with what's called dot recognition, time recognition, and it's not so clear that something like that is part of any of these models. So maybe comment on where is that an agent needs to reach and about what the other guy is trying to do, even in a competitive setting.
Even in a competitive setting.
That's a problem. I'm trying to clean the kitchen after dinner, so we are family. So
that's actually a very interesting question, and you could think, and this is just off the top of my head. You can think of, in that case, you can model observing reactions of some of your observations or what other agents are doing, and then you can integrate this into a regular planning under a certain framework. I observe that you've done something like this. Depends what assumption I make on how you generate your plans. And based on seeing you doing something, I can deduce something about your belief state. That will help me coordinate. Thank you.
Thank you.